be nice, I don't know. Who has heard this quote before? Premature optimization is the root of all evil. Everybody, excellent. Who knows who said it? It wasn't me. I did say it just then, but that doesn't count. Anyone? I think I heard someone. No? It was Donald Knuth, rather famous computer scientist. But as you may be able to tell by my formatting, it's not just that I don't know how to use PowerPoint. It's actually part of a bigger quote, and I think kind of hides the real important story. So the bigger quote is, we should forget about the small efficiencies 97% of the time, but 3% of the time they might be critical. Now obviously these numbers are probably not scientifically derived, but a lot of people sort of will tout premature optimization as the root of all evil as a reason not to do micro benchmarks and not to look at performance until later. And whilst that is good and valid, sometimes it's not. And that's kind of what I wanted to talk about, when perhaps you should do it, and then how to do it, and then hopefully a few interesting gotchas that you might not know about, or maybe you do know about .NET specifically. Now the really keen-eyed amongst you will know that I haven't got a starting quote from my ending quote, because that's actually part of an even bigger quote, which I also like, which is that programmers waste enormous amounts of time thinking about speed of non-critical parts, and what they should be thinking about perhaps is debugging, maintenance, and I would add in there things like readability, all of those things. And that's kind of the thing, is you have to factor in, well, you've got to bring in lots of different factors, and performance is one of them, but not the only thing to just think about. So second quiz question, who knows the name of the paper that he wrote this in? I'm assuming, I didn't know this either. It's actually Structured Programming with Goto Statements, which I think is kind of funny, because this is a paper supporting the use of Goto Statements, which pretty much everyone widely derides now, whilst quoting his quote about premature optimization, which I just think is kind of funny. That's a debate for another time. So, when should you optimize? Essentially, it's all summed up in that one line. You should optimize when you know you need to, and you shouldn't optimize when you know you don't need to. So you should think about optimizing at a high level as well. So you should think about an algorithm before you think about the specifics of the code. So if you've got a function that splits up a string into an array, and then you're going through the string looking for the longest word or something, don't focus on that loop and optimizing that loop that looks for the string and how you're going to do that the best. Think about whether the whole algorithm should be written differently. Should you be splitting the string, or can you use a stream, or can you use a string segment, or use a tree or some structure? Micro benchmarking though is fine if you know the code is on the hot path. And that's kind of the thing there, is if you know that. So once you've determined what the hot path is, if there's a loop that adds two numbers together, if that's the bit that your analysis has said you need to optimize, then go for it, all you like. Draw on your experience, obviously. So we've all got various experience, and we've all been caught out by some things before. Some of those maybe I'll be showing you tonight. That's cool. Draw on that experience, because that is also a factor you need to consider. If you've seen that this thing works 9 times out of 10, don't be afraid to do it, even if your teammates are saying, well, no, that's premature optimization. How do you know it's going to work? You say, well, I've been doing this for 10 years or 5 years or however long, and maybe it will. You can still measure that compared to the other way and actually come up with an answer. And then there's also other benefits of the code that sometimes, even if something looks like premature optimization, well, maybe it's more reusable, or maybe it's written more generically or more readably or whatever it is. And again, there are multiple factors that point into these things. So how do you optimize? There's a few very basic steps. You need to know the context of what you're doing. So you need to know how often this bit of code gets executed and what types of input does it have. Otherwise, you don't know what to look for. You need to question your assumptions. So there's a good example of this I've got later. But if you've got some code and you think, well, the compiler will make this work better. It'll find this string and make it a constant, or it'll unroll this loop or whatever. Maybe it will, but question them and verify them before you just start off down the track. Release builds only. It's kind of like a trap that a lot of people fall into when they write simple benchmarking code, is they forget that they're in a debug build, and anything you find in a debug build, you can just throw it away. It's probably not relevant. At best, maybe it's got the same characteristics of release, but at worst, it'll send you in completely the wrong direction. And you have to measure, and you have to measure and measure. It's the only way to do performance tuning is if you've measured first, change something, measure again, and compare the results. I don't think anybody should be standing there saying, this code is faster than this code, or I'm designing it this way because performance will be an issue. Prove it. You have to measure. So a lot of people start out like this. Hopefully that's big enough for people. Hands up anyone who wants to admit to writing code like this. Oh, nobody, you're all very clever. And if you're so clever, what's wrong with it?
Not using stopwatch.
Very good. Not using stopwatch. So this is using datetime.now. And that's a trap because datetime.now and stopwatch both provide the same level of precision. They both go down to the tick level, which is the highest precision you can get out of .NET. They don't, however, provide the same level of granularity. So if you have a tight loop and you check datetime.now.ticks and a stopwatch.elapsed the stopwatch elapsed ticks will change more often than datetime.now. So don't use stopwatch. Any other things wrong with it? Sorry? Very good. No warm-up. So .NET has compiles to intermediate language, and it has a jitter, a just-in-time compiler. And so the first time your code is run, the jitter will have a look at it and see if it can work out what to do to make it better, which is lovely, but that work takes time. And so this quick profiling method would include the jitting time, which is not, might hide some of your real performance issues. And then the final one is not as apparent, but garbage collection. What else was happening before this method was called? If you get a garbage collection, it's called a GC pause. When garbage collection runs, if that happens in the middle of your loop, that'll take a couple of milliseconds, and that's going to obviously affect the output. So this is the sort of correct way to optimize. Couple of things. So first of all, setting the process affinity to highest, essentially to say, Chrome's going to be running in the background using up hundreds of megs of RAM. Let's try to take that out of the equation as much as possible and devote as much resource to this process as we can. The initial call to the function takes care of jitting. So your first time sort of warm-up, that's taken care of. We construct our stopwatch, not datetime, and then we tell the garbage collector, go and do your thing, try as hard as you can. There's still no guarantees you won't get a GC pause in the middle, but at least you can set yourself up for the best possible success. And then you stop the stopwatch and you output the result. So this is cool. You can use this. But a better way, an even easier way to do it, is to do this, which is to use benchmark.net, which is a open source .NET Foundation supported framework for benchmarking. Has anyone used benchmark.net? A couple. Awesome. So it's really easy to get going. You write a method, or in this case, two methods, because you want to compare two different approaches. You mark them as a benchmark, and you tell it to run. And that's it. That is as simple as it can be. There's a few more features we'll get to in a minute, but this does all of the work for you, and it does it in a super reliable way. How it works is rather detailed, so this is a brief discussion, but essentially it generates a separate process to run your tests. So we're fully separated from whatever else your code was doing, although you probably shouldn't be doing much else if you're running a benchmark. And what it does is it runs your code like heaps of times, and it does a few different things. So first up is the pilot stage. And so what it does is it runs your code and it tries to determine how many times it should call your method. And it essentially has a target it wants to achieve of how long the code should take. So it wants to run, 15 runs, and it wants to take 10 seconds per run to get a good measurement. So it'll determine that it needs to call that method 1,000,000 times or 1,000 times or however it is. Then it does some warm-up, and it runs your code in idle mode, which is to try to calculate how much overhead it adds to the process, because obviously measuring affects how long your code takes. Then there's the main warm-up, which is to let the jitter do everything. And then main target is when it actually takes all of its measurements and it actually times your code. And then the result is how long that took minus the average overhead that it calculated in the first step. And then it does that whole thing multiple times for everything you want to report on. So if you want to report on timing, or timing is the default, so you always get a report on timing, it's going to run that once. If you also want to report on memory usage or how many times garbage collection ran or any of the other diagnoses that it has, if it put them in that first run, obviously that would affect the timing as well, so it runs them separately. What this all means is, after I've now finished telling you why benchmarking is bad, and we're going to do some, we're not going to do any because it's too slow. Running a decent test on benchmark.net, just to compare even a couple of things, it does take a while. A couple of minutes. Not a very long time, but a bit boring and a bit long to watch on a demo. So these are some I've prepared earlier. So I thought I'd go through some of the maybe gotchas in .NET, or maybe things you already know in .NET you know to avoid. We'll see. So the first one is string.join versus link versus string builder versus concatenation. So essentially computing a CSV list of a CSV string out of a list of numbers. So this is the setup code for benchmark.net. So memory diagnoser at the top, that says I want to track memory usage, which, as I said, that's going to start a whole other run when it gets to it, and it'll track memory usage. The rplot exporter gets us pretty graphs done with R, with the statistical analysis library. And then we have a couple of interesting things. So the params attribute is a really good one for making sure your benchmarks cover a bunch of scenarios. And if you've ever used XUnit, this is a lot like a theory, where you provide theory data. So benchmark.net will run this, all of the benchmarks in this class multiple times, once for each parameter. So it's going to run it 1, 2, 3, 4, 5, 6, 7, 10, etc. If I had another parameter with another params thing, it'll be every combination thereof. So you can really get the full coverage of all of the possible variations of your algorithm to really hone in on when it's good and when it's bad. And then setup is, again, similar to test frameworks where they've got class initialize, test initialize, that sort of thing. So setup is going to be run once before it runs all the benchmarks in this file. And so all that's doing is creating an array of the right size and then filling it with random data. So after this, before our benchmarks run, we're going to have an array with random numbers in it, random bytes. That's it. So these are the actual benchmarks. And you can see they're just very simple methods tagged with a benchmark attribute. Two things to notice here. Number one is the baseline equals true over in the top left. And that's optional, and what that does, if you include it, is it just means that in the results, benchmark.net's going to show you how all of the other methods compare to that method as the baseline, which just means you get a really easy way to say, well, if the comparison is less than 1, then the other method is faster, and if it's more than 1, then it's slower. It's optional, and it doesn't affect how the tests run. The other thing to notice there is that the methods are all returning a string or returning something. And that's important to avoid some of the optimizations that C# has and the jitter has. Sometimes if you don't return anything, depending on what is happening inside the method, the jitter will just recognize that your method has no side effects, remove the whole lot, and your benchmark is now useless. You'll get one that runs super fast, one that runs slow, and you might pick the wrong thing. So it probably wouldn't have happened in this case, but it's always good practice to just return something out of a benchmark. And so we have standard concatenation, using a string builder but initializing its size, and string.join, and then this one is using links aggregate method, which I personally had never used before, but actually this example came from some production code at work where instead of using string.join, someone used string.aggregate or data.aggregate. They were in a bit of a link mood, and that's what caused this whole talk really to start. So,
I'm guilty.
well, does anyone want to have a guess before we go to the next slide, which has some pretty pictures?
String.join might be very good, or the string builder.
All right, so yeah.
It's very smug.
Everyone, I'm pretty sure knows that string builder, string.join, they're going to be the best ones. They wouldn't be on the slide if they weren't. So, I've done something. Oh. Oh, there we go. That was weird. Okay, so yeah, so string.join, string builder with capacity and string builder without are all sort of, similar level, and aggregate and concatenation are obviously higher. Interestingly, this is taking a long time to update. So for the first run, concatenation actually wins. And that's because that is a run with one string. And of course, if you're concatenating one string, well, so concatenation works then. But as soon as we go to 2, it'll jump up in a minute. I've pressed some button. As soon as we go to 2, string builder wins. When we go to 3, string builder still wins. Interestingly, it wins by more, I think. Like, I don't know, that's a bit anecdotal. But then once we get to 4, string builder with the initial capacity is the winner. There it is. Just a tiny little bit. But that trend continues on. And essentially that's the winner now. There is this sort of odd one over here somewhere where this one's better than here, but the rest aren't. It's a bit strange. This sort of brings up a point about context. You have to know what is the scenarios you're benchmarking. So this is up to 10 elements in the array. And so if your code is usually processing around that many elements in a row when you're producing a CSV string, because we all have code that does that, then, string join, builder, whatever. If you want absolute fastest, go string builder with capacity. That's easy. But as you get more data, the differences start to really stack up. So if you process 100 elements in the array, we're now getting about, twice as good from these 3. And what you can see is if you're processing around about 100 elements, it kind of doesn't matter whether you use string join, string builder with capacity, or string builder without. If you go to 1,000 elements in the array, in a second, there it is. And now we're getting, much bigger. So you can see basically this is on an exponential path and this is on a log path. So, much better performance. If you go to 10,000, it just gets silly. So now what that lets you do though is that lets you be a little bit pragmatic, right? You don't have to say, oh, no, you should use string.join, don't use string builder, because string.join is better, or string builder, but make sure you initialize it or whatever. If you're going from string concatenation to any one of those 3, the differences are going to be so huge that you've solved the problem essentially. You don't need to focus down to that distinct level if you know that this is the type of data you'll be processing. So that's where you really need to know your context. The other interesting thing I didn't cover there is memory usage. And so again, this example comes from some production code where someone was building up a string to describe a function based on the environment, the platform, and the customer, I think. So it was 3 strings. Any one of them could have been null. And it was simple. If this isn't null, add it to the string. If this isn't null, add it to the string. And it was just using string concatenation. And my gut feeling was, well, no, let's use a string builder. So these strings are about 20 characters long. So string builder, 120 nanoseconds, concatenation 267 nanoseconds. So string builder is definitely faster. But interestingly, for that size data, concatenation uses less RAM because there's an overhead to constructing a string builder. Now, we're talking 213 bytes. It's not a lot, but you never know. Maybe that's important. And again, it's how often does this get called? If this gets called a lot, and perhaps you have an app with a memory problem, well, you might want to trade off some speed for memory if you know this is the type of data you're working with. If we increase that to 2 million character strings, string builder now is the clear winner on all fronts. So you've got to know where your data's running, and you've got to know what your context is. The thing to note with the 126 nanoseconds and 267 nanoseconds, and this is an awesome feature of benchmark.net that it can even get out these numbers, because on the machine I ran these on, the granularity of stopwatch is 300 nanoseconds. So in production code, if you were timing, you wouldn't even see any difference there. And so that's where you've got to think about, is this performance gain worth it? Do I want the memory gain? In this case at work where this came up, we actually just said, well, you know what? String concatenation here, it's just much more readable and it's much more debuggable. And, we were thinking, well, if we had this as a generic method, you could loop through the elements and then you have construction of an array overload and you've got loops. And so you've really got to think about it before you go. You can easily sort of go down the rabbit hole of trying to solve a problem that maybe doesn't really exist. So the next example is dictionary versus iDictionary. I have no idea whether, well, there we go. So has anyone heard of this in terms of a performance trap? Cool. This was an interesting one I thought too. The test here is really easy. Constructing one dictionary and then just storing two references to it, essentially. One as an iDictionary and one as a dictionary, and then looping through the dictionary and doing nothing else. So this is an empty dictionary and just looping through and not executing any code. So the numbers here are going to be small because we're not doing any work, but interestingly, the difference is actually, like, percentage-wise, kind of huge. So an iDictionary enumerator takes twice as long and allocates, well, okay, 32 bytes, but compared to 0, that's a lot. And if you had data in the dictionary, or perhaps were doing some work in that loop, you know, this bar chart might go up a lot more. So this was an interesting one to me, because when you talk about questioning assumptions and trade-offs and that sort of thing, you know, generally speaking, coding to interfaces is seen as better, full stop. However, if you have a performance problem and you have a hot path that does lots of looping through dictionaries, you might want to break that rule in order to gain some performance. Essentially, the overhead here is the dictionary enumerator is a struct. So when you enumerate through dictionary directly, you get the struct. It's all, you know, within your little bit of memory and it's all cool, no boxing, whatever. The iDictionary enumerator comes through IEnumerables implementation, which returns a class, which returns, well, it's an interface. Essentially, it has to box that enumerator. So your struct that was now nice and small and compact and built for performance now gets boxed by .NET, and now it's essentially a value type. So you have that overhead. All right, so next up, loops versus link. I'm an old man, therefore I like loops, and the young people at work like link. And sometimes I say, no, don't do that, that's terrible. And sometimes I say, okay, that's fine. This is one where you really have to think about your trade-offs because of how much more readable and expressive link is. But so, really simple example, we're looking for number 5. There's a first or default with a predicate and a where with a predicate, then first or default, and just old school loop. And this one, it's not very surprising, I guess, because I wouldn't have put it here if it didn't look like this, I guess. The interesting thing here is just the difference between these two, because I see a lot of people at work, you know, that's a very stylistic thing. Most people would think where and first or default versus just first or default's kind of style doesn't really have any impact, but it does because it's more allocations and more function invocations. So again, if it's on the hot path, maybe it's something to think about, maybe it's not, you know. And then, yeah, if you iterate through, it's just nothing. And that also is partly because of the jitter. In this case, there's probably some optimizations that the compiler is doing to unroll the loops or to do branch prediction or I don't know what, that obviously it can't do when you're talking about funcs and expressions and etc. And then one that I'm sure won't be surprising to anyone, what the answers are, but exceptions versus not exceptions. Everyone knows exceptions are slow, right? Good. But how slow? And is it important? So really simple. Again, test int.tryPars versus int.pars. Obviously, hopefully no one's using int.pars with a catch, try catch around it, but you never know. Just as an example. And then random data where 50% of it, well, sorry, there's a 50% chance of it being not valid. Now, I put this here also partly just to illustrate with benchmark.net. That global setup is going to be run once, and then both benchmarks will be run against that data. So even though this is using random and different runs might give you different results, for a single run, you are still comparing apples to apples within the benchmark. And then the results are probably not surprising to anybody because there is a line here for trypars, and then it's like 49,000 nanoseconds. So again, this isn't long. You know, we're talking nanoseconds. 408 bytes allocated though is actually kind of big if you think about that compared to how many bytes were allocated for a where or a func, which was like 30. For the string builder was about 26 bytes. So that's capturing all the stack trace. That's capturing, you know, all the execution context. Now, this is in a class with one method, so it's a very small stack trace. Still got to capture all that. So don't use exceptions for control flow. I hope you've learned something. And hybrid dictionary, I just wanted to throw this in here because I liked it. This is a screenshot direct from referencesource.microsoft.com of their hybrid dictionary. And I like this for two reasons. Number one, it reminds me of the XKCD comic where the random number and it just says return 4. This is the type of thing that I think is really cool to see though. So a hybrid dictionary, in case you don't know, because it's a bit of an underused class, it will use a list to store things, or it will use a dictionary depending on how many things it has to store, because one is more efficient at lower numbers and one is more efficient at higher numbers. The number is 9. As soon as you have 10 things in a hybrid dictionary, it's going to use a dictionary. You may as well just use a dictionary. And I really like this because it shows thought that has been put into the framework, like that's nice of them. And I just love the comment. This is like, I know this looks like a 9 and it's random, but trust me, we've done some work to work out this should be a 9. So, and same thing with string builder versus concatenation. That magic number for where you should switch over, it's about 4. That's what I sort of discovered on my machine, but you know, yours might be different and all those things. But it's just something that, you know, if Microsoft think about it, we probably should too. So in summary, should you always use dictionary instead of iDictionary? Should you always use struct instead of classes? Should you always, etc., etc., etc.? No, of course not. It depends is always the answer, except for this. If you know how to initialize a list with capacity, just be nice. Just go on. Tell it the information it wants. But generally speaking, you know, the key thing here is it always depends. There is no this performs better than this because it depends on what types of calls you make. It depends on what you're trying to get out of it, whether it's RAM or whether it's speed. When you talk about, you know, if you've got something in the cloud, if you've got Azure Functions, you want it to be as quick as possible, great. If you've got a long-running MVC web API thing, it's going to get killed if you use up too much RAM. So you might have to make some trade-offs. And then you've got maintainability and readability and all those things. If you have code that you know you're writing and no one is ever going to look at it, then use an unsafe block, use a string pointer, and just stream through that data, no worries. But the old, you know, the maintenance programmer is an axe-wielding psychopath, maybe think about something else. That's it. Any questions? Cool. Thank you.